Imagine your application is processing thousands of requests perfectly, and then traffic suddenly backs up. Response times skyrocket. But when you check your monitoring dashboard, the error rate is completely flat at 0. This silent traffic jam is often caused by a small piece of code called sync.Mutex. Behind the scenes, the mutex operates as a hybrid machine that monitors itself and changes its own rules under pressure. Understanding the mutex starts with this compact 8-byte data structure. It is made of two parts, a 32-bit number called state and another 32-bit number called a semaphore. That single state number holds the entire configuration. The first 3 bits act like light switches, showing if the lock is held, if someone is waking up, or if the system is starving. The rest of the number is a counter, tracking exactly how many tasks are waiting in line. Code solves invisible latency cliffs by modifying the bits in this single integer. To claim the lock, the computer uses a specialized, unbreakable hardware operation called compare and swap, or CAS. This uninterrupted move checks if the lock is free and grabs it at the exact same instant, preventing anyone else from sneaking in. When goroutine A, a lightweight task in Go, arrives at a free lock, it uses that CAS move to instantly flip the locked switch from a 0 to a 1. This is the fast path. If goroutine B arrives while the lock is already held, its attempt to grab the lock bounces off the state box. At this point, goroutine B enters a spin phase. It runs in a tight loop on the processor, checking the lock up to 4 times, hoping goroutine A will finish its work quickly. This spinning is only permitted on multi-core processors when another core is available to do work. On a single-core machine, spinning is disabled because the task holding the lock needs that same core to finish its job. Spinning briefly on the CPU is an intentional trade-off. It burns a few cycles because it is much cheaper than the heavy cost of putting a task to sleep and waking it back up. Once a task exhausts its spin budget, it must park itself and yield the processor so other work can get done. Goroutine B moves into the runtime semaphore. This is an organized, branching waiting list where dormant tasks wait their turn. It finds its spot and goes to sleep. When the lock opens, the system signals goroutine B to wake up. However, a brand new arrival, goroutine C, is already running on the processor. It bypasses the waiting list and grabs the lock before the sleeping task can react. This is called barging. To stop this, the lock uses a 1 millisecond timer. If any task waits longer than that, the starving bit flips to a 1, triggering a total rule change. In starvation mode, the lock disables barging and spinning. New arrivals are repelled and sent to the back of the line, while ownership passes directly to the task that has been waiting the longest. Barging keeps the system speed high by keeping the processor busy, but it creates a fairness risk. A sleeping task could theoretically be skipped forever by a constant stream of new arrivals. The Go runtime makes this sacrifice on purpose. It gives up maximum speed to guarantee that every task is treated fairly, which prevents long delays for individual requests. Because the entire lock is just 8 bytes of memory, passing a copy of a lock-containing structure to another function creates a serious bug. You end up with 2 independent locks guarding the same data, leading to silent corruption. The mutex also lacks an owner record, meaning it doesn't know who is holding it. If a task tries to lock a mutex it already holds, it fails the check, goes to sleep in the waiting list, and waits forever for itself to finish. This chart shows how these failures present in production. The red line representing lock wait time is rising, even though the error line stays at 0. Monitoring this wait time metric is the only way to detect a lock bottleneck before it impacts users. High lock contention is solved by changing data architecture. The standard approach is the sharded lock. A sharded architecture divides data into smaller sections, giving each its own independent lock. This allows multiple tasks to work on different pieces simultaneously, clearing the bottleneck. Scaling a system requires moving beyond simple commands and understanding how the Go runtime balances speed against fairness. Mastering these 8 bytes is the key to building truly resilient software.